Welcome back, class. So, in today's lesson, or in this lesson, I want to talk about applying some of the ideas that we talked about in Chapter 2 in terms of quantifying matter, in terms of, we talked about the mole and quantifying atoms. I want to apply some of those ideas to compounds and molecules. So let's start with a little vocabulary. So we have, of course, two different masses, just like we did for atoms. So for atoms, we had what was the atomic mass, right? The mass of an individual atom. We have what's called the formula mass, which is the mass of an individual molecule or formula unit, if we're talking about ionic compounds, and units of AMUs. Right? So this is the analogous thing to an atomic mass of an element, right? It would be the mass of a single molecule or formula unit in units of AMU. Of course, just like we had a molar mass of elements, we can have a molar mass of compounds. So this is the mass of 1 mole of molecules or formula units. And this is going to be in units of grams per mole, just like we saw when we had the molar mass of elements. Now, how do we obtain the formula mass or the molar mass? Well, we simply add up the atomic masses or the molar masses of the individual atoms in our compound. So, for example, if I have water and I want to calculate its formula mass, so I need to add up the atomic mass of 2 hydrogens and 1 oxygen. So I'm going to take the first element, and I have 2 of them, and I'm going to times it by I'm just going to use 2.01 here, AMU for hydrogen. And then I'm going to do the next one. So I only have 1 oxygen. So that's 16.00 AMU. And, of course, that's going to equal 18.02 AMU. Right? And that's going to be the formula mass, or the mass of 1 molecule of water. Now, if I want to do the molar mass of water, it's going to be the same idea, except instead of using the atomic masses, I'm going to use the molar masses of the elements. So 2 times 1.01 grams per mole for hydrogen, plus 1 times 16.00 grams per mole oxygen, and I get the same numeric value, but in different units. So just like there is the same relationship between the atomic mass of an element and its molar mass, right? They're the same numerically, but with different units. The same thing works for compounds, right? The formula mass and the molar mass are numerically the same, but in different units. The molar mass being in grams per mole, the formula mass being in AMUs. So we can apply all these same compounds, or all these same ideas to compounds as well as elements. So now let's move a little further and look at how we apply some of the mole concept ideas that we talked about. So just like I maybe wanted to convert from grams to atoms or grams to moles, right, for an element, I might want to do the same thing for a compound. So I have the ability to convert between grams and moles of a compound, again, using the molar mass of that compound, and to convert from moles of molecules to individual molecules, and just like we did it, anytime we want to convert from moles to individual items, we're going to use Avogadro's number, or the number of individual items in a mole. So 6.022 times 10 to the 23rd molecules of CO2 per mole of CO2. So we can work with these just the same thing as we did with atoms. So if I want to know how many moles of carbon dioxide are in 0.62 grams of carbon dioxide, I'm going to set it up in the same way that I would have before. So I'm going to start with what I know. And if I want to convert from grams into moles, right, the key is my molar mass. So I'm going to have grams on the bottom because I want to cancel out my dimensional analysis. And on top, I'm going to have moles of CO2 because that's my desired unit. And how I need to know the molar mass of carbon dioxide. So I'm just going to go up here. And so for CO2, I have 1 for carbon, so that's 12.01 grams per mole, plus 2 oxygens, so 2 times 16.00 grams per mole. And if you add all that up, you get 44.01 grams per mole as my molar mass. So I'm going to plug this in, and that 1 mole, 44.01 grams. So of course here my grams of CO2 cancel, and then I do my math, and it turns out that I end up to 2 significant figures, 0.014 moles of CO2. Yeah. Well, what if I want to say how many CO2 molecules is this equivalent to? Well, I can go between moles and molecules again, using Avogadro's number, right? That's how we go between individual items like molecules into moles or vice versa. So I'm going to start here again with what I know, my 0.014 moles of CO2. And so how many molecules of CO2 does that represent? So my units are going to have moles of CO2 on the bottom to cancel, and I'm going to have molecules of CO2 on the top. And there are 6.022 times 10 to the 23rd molecules of CO2 in every 1 mole. My moles of CO2 cancel. So then if you do your math, again, limit to 2 significant figures, you come with 8.4 times 10 to the 21 molecules of CO2. So any of those mole conversion type calculations that we learned about in Chapter 2, we can apply those just the same to compounds, either molecules, or if we had an ionic compound, we would have the unit of formula units, right? But the calculations would be identical. Now, one sort of additional thing that we like to do when we're dealing with molecules is to see if we can break it apart, if we can figure out how much of each element there is in the molecule. So break down the molecules into the parts, right? And to see what percent of it comes from this element, what percent comes from this element, etc. So we can do something called mass percent calculation, or mass percent composition. So essentially how we calculate this is, if I want to know the mass percent of some element, I'll just say X, it's going to be the mass of element X in the compound over the molar mass of the compound times 100, right? Because I'm going to be a percent. So essentially what we're doing is we're taking the part, right? So how much of the mass is coming from element X divided by the total mass? So the part over the whole, right? What any percentage is, right? And the fraction times it by 100 to convert it to a percent. So let's do an example. So let's say we have the compound CCl2F2, and we want to know what is the mass percent of chlorine in this compound. Well, I need to know two things, right? I need to know what the molar mass of this compound is, and I need to know how much of that molar mass is coming from chlorine. So let's calculate the molar mass first. So the molar mass of CCl2F2 is going to be 1 carbon, 12.01 grams per mole, plus 2 times chlorine, which is 35.45 grams per mole, plus 2 times, 2 times the mass of fluorine. And if we add all of this up, we end up with a molar mass of 120.91 grams per mole. So now I can write out my equation for the mass percent of chlorine, and it equals the mass of chlorine in my compound is CCl2F2 divided by the molar mass of CCl2F2 times 100. So I know the molar mass is 120.91 grams per mole. Now how much of that is from fluorine or chlorine? Well, I know there's 2 chlorines, so that's going to be 2 times the mass of chlorine. But all I have to do is sort of look at, I've already sort of done this because I have the parts here, right? So I have 12 from the carbon, I have 2 times the 45 grams per mole. So if I have that, this is going to give me 70.90, right, as the amount coming from the chlorine. So we're going to have 70.90 grams per mole times 100. And this equals to 4 significant figures, 58.64% chlorine. So we know this compound is 58.64% chlorine. And we could go by and do this for any element, right? We could continue to break this down, and we could find the mass percent of carbon by taking the 12.01 divided by 120.91. We could find the percent of chlorine by taking the 2 times 19 and dividing it by 120.91. And if we were to get all of those percentages, they should add up to 100%. Now, once we know the percentages, right, if we know the percent composition, then we can do something like what we have here. And we can figure out, well, if I have a sample of this compound, how many grams of that sample are coming from chlorine? Or how many are coming from fluorine or carbon? Right? So the way I'm going to approach that is I'm going to have here the mass of my compound. Now, the key here is to understand a little bit about percentages, right? So a percentage is out of 100, right? So what this really means is that in a sample here, that 58.64 grams of chlorine per 100 grams of compound, right? So when we put these in percentages, it's telling me how many grams out of 100 are coming from this particular element, right? So if I have 100 grams of compound, 58.64 grams of that is going to be chlorine. So I can do it this way. I have grams of CCl2F2 and grams of chlorine. Right? So 58.64 per 100. And if I do that, I get 2.199 grams so let's cancel grams of chlorine. Now we have three significant figures, so this becomes 2.20 grams of chlorine in this sample, right? So of this 3.75, 58.64% of it is coming from chlorine, and that represents 2.20 grams. Now, if you're more comfortable, you could also do the calculation like this, just as an alternative. I could take my grams and I could just multiply by the percentage. So I'm going to write it as a fraction here. So I could, since I know that it's my percentage, then this would give me, again, to three significant figures, would give me the same idea, right? So we're doing the same thing here. Here we're just using our dimensional analysis and spelling out that this is 58.64 out of 100. Here we've done this part of the calculation and we're just multiplying by that percentage written as a decimal. So mass percent composition, right? A useful tool to allow us to break down a compound and figure out how much of that compound is coming from the individual elements within that compound.